Okay, off we go. So here's where we were last. Oh, don't forget about the attendance quiz, attendance code. I only put this up here a few seconds ago. Sorry about that for the late add of the number. Anyway, make sure to do that. Clock's ticking. Here's where we were last time. We were talking about this, what to do if there's a singularity with your vector field. And just a reminder, everything that we've written down so far about Green's theorem assumes that everything in sight is as regular as we might need it to be, that there's no, discontinuities, everything's differentiable. And for most of what we're going to be interested in, that's going to be the case. But sometimes there will be singularities, and there are a few particularly important such cases. This is a good sort of segue into those kinds of cases. So let me remind you what we've already established. So we talked about this vector field right here, and of course you can see it blows up at the origin. There's a serious problem. It's not even defined at the origin, right? And as you approach the origin, the vector field gets greater and greater in magnitude. So I wouldn't call it an asymptote, but something big, some sort of explosion happens at the origin. Okay, but everywhere else the curl is 0, right? So everywhere else the curl is 0, and it's tempting to say that, well, who cares about one little point? It's just 1 point. What's the big deal? How much problem could a mere 1 point cause? All right, well, here's the other thing we did. We speculated, shouldn't all these circulations be 0? If we really believe that 1 point can't cause any problem at all, we'll basically ignore it. Curl is 0 everywhere else, and so it seems like we ought to get 0. But if you actually compute these line integrals, you don't necessarily get 0. You get 2 pi times the winding number, how many times you go around the origin. And so in particular for this curve right here, oriented that way, we go around the origin once, the winding number is 1. That line integral is 2 pi. It is not 0. Right? So this little theory about that 1 point not mattering, okay, well that just blew up in our face, right? It clearly doesn't work. That one little point has caused a severe catastrophe. Is that cool? Everybody with me? Okay, now a couple of things. I do want to persuade you that this formula here is actually true. I'm going to basically just point to how y'all are going to confirm this for yourselves. You can first, just as a warm-up problem, just take some circles centered at the origin, parameterize those circles, and confirm that those circles, of course, go around once. You can compute the line integral and you'll get 2 pi. That's pretty straightforward. Good exercise. I encourage you to do that one. But more specifically what you can do, and let me zoom in so we can see better. If I can get this to cooperate. There we go. If you look at f dot dr, it turns out that f dot dr is d theta. So when you're doing integrals along these curves, when you're doing an integral of f dot dr, what you're doing is you're doing an integral of d theta, namely you're just keeping track of how much theta changes as you go around the curve. And so with that in mind, it's a pretty straightforward argument as to why you get 2 pi k, because, for example, for a curve like this one, you can see you go around 1 time. Let's keep track of what theta is doing. If I start here, theta is 0. As I move around, theta increases. I go around a total of 1 time. Theta has increased itself all the way up to 2 pi. And I get 2 pi. And if my curve went around twice, theta would have increased by 2 pi twice. And I would get 4 pi. And etc. So that's how that argument works. Now, how do you know that this is true? How do I know that f dot dr is d theta? That is an exercise that I want to encourage y'all to do for yourselves. You can take this old polar coordinates equation, y over x equals tan theta. Just take the differential of both sides, and you rearrange things a little bit, and you'll get exactly this. So give that a try. If you get stuck, come talk to me. I'm happy to show you. It's like 3 lines. It's not that big a deal, but you do have to kind of set it up just so. Anyway, give that a try. Okay, so here's now what we're sort of left with. We have this we have to confess that we can't really cite Green's theorem. Green's theorem just doesn't work. You can't compute integral of curl if curl isn't even defined at the origin. Okay. Okay, how about this? Is there a more intuitive sort of takeaway recovery that we can make? And here's what I claim we can still do. I still claim that we can think of the circulation, right? The circulation that we have looking at that closed line integral. I can still think of that as being distributed through the interior. I just have to think about it in a different way. So curl, recall, is how you describe when this substance, what we think of as a kind of a stuff called circulation, is distributed in a kind of a continuous manner. If you have stuff per unit area, that's distributed. And it's perfectly fine to continue to think of, around here, right, everywhere except for the origin, perfectly fine to think of, there's just no stuff there because the stuff density is 0, and absolutely. So how do we make sense out of the idea of there being then a total amount of stuff being 2 pi? And the answer is, we're going to imagine that at the origin, it's like there's a lump, not continuously distributed, but a lump sum amount of this substance. Again, this substance is called circulation. It's like there's a lump of this circulation at the origin. Now that's kind of a weird thing to talk about. Let me remind you, it's already weird enough to think of circulation as being a substance. That's already strange, right? And now I'm asking you to imagine that there's a finite amount of that stuff at a single point. Let me just remind you, in physics classes you may have taken in the past, you may have already seen the idea of a point mass or a point charge. Do y'all remember seeing point masses and point charges? If you ever write down the formula for the electric field created by a charged particle, well, it's written assuming that is a point charge. Likewise, gravitational field created by a mass. They always write it down assuming that it is a single point mass. It's not physical, but the point is it kind of behaves that way even if it isn't actually physically the way it is. So this is the same sort of thing. It may be a little hard to imagine, a little counterintuitive. Think of there being a point, not a point mass, not a point charge, but a point lump of circulation. Same kind of an idea, and again, still a little bit weird, but it totally works. It totally gives us what we need. And let me just try to persuade you now that this totally works for our purposes. Oh, let's go back to here. So for this curve C2, can I say that the circulation measured by computing around the boundary, is that the sum of all the circulation in the interior? Well, in the green area, there's no circulation, and then there's a lump of 2 pi, grand total 2 pi. Cool, that's what it's supposed to be. Now let's look at the curve C1. The curve C1, like this. Now, of course, it's got an interior. The curl is 0 everywhere except the origin. So the curl is 0 in this whole green area. Now, does this work? Can I think of circulation being distributed as previously described? Well, if it were, then for this curve, this C1 curve, well, let's see. What's inside of the curve is nothing. There's no circulation. There's still this lump of circulation at the origin, but that's not inside the curve. right? So this would have me computing that C1 line integral is 0. Is that correct? Look at that curve, and let's think how many times does that go around the origin? Well, it doesn't go around the origin at all. The winding number of that C1 curve is 0. The value of that line integral is 0. And again, it works. Right? So this is something that's actually going to work every time. It's again, a little bit of a weird sort of takeaway, but this little metaphor of imagining that yes, there is a stuff of circulation, and it's all concentrated at the origin, a single lump in the amount of 2 pi, and all of these integrals work out accordingly. How are we doing? Is everybody okay with that? So we're going to see some similar things when we get to Stokes' theorem and Gauss's divergence theorem in Chapter 7. This is kind of a warm-up sort of starter example, and I think it's kind of a nice example of how you can treat such situations in some cases. Okay. Alrighty, moving along. That does it for 6.2. On to 6.3. We have a new big theorem. Here's the big theorem. It's called the fundamental theorem of line integrals. You'll recognize probably the structure of this theorem. There's the iconic f of b minus f of a, right? It looks just like the fundamental theorem of calculus. Integral equals f of b minus f of a. I mean, come on, it looks just like it, right? Notice furthermore, the integrand is a derivative. In this case, a gradient. And notice furthermore, the thing whose gradient, I can't use that color, I already used it. The thing whose gradient you're talking about is what you plug into at the end. Right, so structurally, this is just like the fundamental theorem of calculus. Now, there's different ways to prove this, and if our goal was to prove it as efficiently as possible, I probably wouldn't do what I'm about to show you. That is not my goal. My goal is to show you how this theorem and previous theorems that we've talked about and future theorems we're going to be talking about can all be viewed in the same way, and that's this point of view about accumulation. Right, so I'm just going to make the same observation that we've made before, and that is that change is an accumulating quantity, f of b minus f of a. The idea of how much something changes has this feature of accumulation. We've talked about that in the single variable context. Now I'm going to point out, even along a curve, it still works. Right, so by the way, my metaphor here, what I like to think of when I'm looking at a situation like this, I imagine that this is a windy mountain road. I imagine that the function f, the thing whose value I'm keeping track of and how much it's changing, that's altitude in my mind. That's just my metaphor. That's what I like to think of. So imagine altitude as we're moving along that curve, and question is the total change. Is that the sum of my altitude change on the first part of the drive plus my altitude change on the second part of the drive? And, well, let's see here. That cancels with that. And sure enough, we are left with exactly what we're supposed to get. Everybody good? So, sure enough, even if you're talking about how a function changes along a curve, yeah, still change is an accumulating quantity. The whole is the sum of the parts. It's all over but the details. Okay. By the way, I'm also going to point out, I think this is just worth marveling over the familiarity of it. This cancellation that happened. All right, we've got that minus sign there. Well, what that is saying is that the shared edge appears twice in this computation, but with opposite signs, and so they cancel. Does that sound familiar? That's exactly what happened when we were talking about Green's theorem for circulation. That's exactly what happened when we were talking about the two-dimensional divergence theorem for flux. these shared interior pieces and shared interior boundaries always appear twice with opposite signs and therefore cancel. So the analogy is just bonkers strong. Okay. All right. So that means we have an accumulation theorem. We just have to figure out the corresponding density. Flashback to chapter 2. Right? Dot product with the gradient is how you turn input changes into output changes, right? So dr says how far I move in the domain. This, what I'm calling d delta, how much, what's the little piece of, how much change do we have, right? Change is a total thing, and d delta then represents how much of that change happens as a result of this one little change in the input. So dot product with the gradient does that. Again, chapter 2. Does everybody remember that from chapter 2? Okay. And then we're going to rewrite dr as t times ds. And this is the little detail that gives us what we actually need. This now is our density, because that expression is what we multiply by size, namely, how long is that little piece of curve, to get how much of our quantity in question, how much of our accumulating quantity, how much change do we get as a result in the output. Right? So what I have in purple is stuff in blue per unit size in green. And it's all over with the shouting. That's our density. Again, we make the argument that change is an accumulating quantity. The whole is the sum of the parts. And then again, on any given little piece, we have gradient.t times ds. And there's our theorem. How we doing? Is everybody okay with this? Okay. Now, just a quick notational point. I wrote it as, dot dr in the original statement of the theorem. I do like that notation. I think that's ultimately a little bit better of notation. So here we go again. T times ds is dr. We'll just kind of put that back in there. And here's the sort of more familiar, previously stated version of the theorem. Okay. Now, a semantical point that we don't technically need right now, but it's going to pay off big later. So I just want to plant a thought for you. As we've already discussed, that is our density. Change is the quantity in question. So that's what we're going to call our change density gradient dot t. Now I want to ask a related question. Not gradient dot t, but what about just the gradient? How should I think about just the gradient? And I can't say that it's change density because it isn't. It's not even a scalar. It's a vector. Right, it's the wrong kind of critter. I mean, a density needs to be a scalar because you got to multiply it by a scalar size to get a scalar quantity. Gradient's not a scalar. All right, so what's the way to think about this? And the following is going to sound a little bit weird. I think this actually makes lots of sense, though. I'm going to first try to persuade you that dr you can think of as being, I'm going to call it oriented size. I know that sounds weird. But let's think about what the dr vector is. There it is. The dr vector, well, its magnitude is literally the size. But it's a vector. It also has a direction. What is that direction telling me? It's telling me literally the orientation along the curve. So dr has two factors, one of which is orientation, one of which is size. I think oriented size is a reasonable term to call it. So with that established, and keeping in mind the stuff that we're interested in, we need to think, what is the thing that we multiply Not what do we multiply by size to get stuff, that would be density, but what do we multiply by oriented size to get stuff? And I argue, I think a reasonable take is that you can view this as being an oriented density. So I'm going to call this oriented change density. Now again, let's talk through how this is a reasonable take. What do we already know about the gradient? Its magnitude tells us how steep the hill is, right? From a graph point of view. The magnitude of the gradient tells us how much change per unit distance traveled horizontally. The magnitude of the gradient is telling you change per unit size in the optimal direction. So density kind of makes sense already. It's giving you stuff per unit size just with the understanding on the assumption that you're going in the optimal direction. What else does gradient tell us? Well, gradient points in a direction. And it points in the direction that is uphill. It points in the direction that change is most sort of fundamentally happening. It points with an orientation describing, again, what's the optimal direction, what is the direction, and what is the uphill direction. So I think this term actually makes sense. Now, this is a really weird idea, and I totally grant that the idea of having a vector that I think of as a density is pretty weird, but the pieces do kind of fit together in a pretty reasonable way. So again, let's think of this now not as a scalar density times a scalar size. Let's think of this calculation as a vector oriented density times dot a vector oriented size. Okay, now I'm just planting that thought. We're going to come back and talk about this again later on when we get into Chapter 7. We're going to talk about something called Stokes' curl theorem, and the big question, one of the most challenging aspects of the course is to get a good geometric sense of what does curl look like? How do I visualize curl? And this is going to be a foot in the door for that. So again, we'll revisit all of these ideas later when we get into Chapter 7. Just wanted to plant the thought, get you kind of stewing on that, and then we'll come back and talk about it again next week or whenever that is. Okay, let's do an example. Reminder, here's our big theorem. This is the theorem we just talked about. If you want to compute an integral, the integral is f of b minus f of a. You just have to make sure that your vector field is a gradient, and you got to make sure that you know the anti-gradient, because that's what you're going to plug into. Okay, so here's our question. Now, before I show you the solution, I want to remind y'all, I think this is a really important sort of philosophical point about how to think about certain things. This is not a plug and chug type of question. You'll notice it didn't say compute this line integral by a particular technique, right? You can compute this line integral by whatever technique you think makes your life the easiest. And we've got several possible options. I mean, one thing you could do, the curve is pre-parameterized. You could pull back through the parameterization and plug and chug. And you'd have I'm going to call it an inconvenient trig integral would result. It's doable. It's not convenient. We don't really want to have to do that. Okay, so here's another thing you could try. And by the way, it wouldn't work. But something you could try. Green's theorem. Right? That's our recent, before today, our most recent cool theorem for how to compute line integrals. The problem is the curve would have to be a boundary. And we're about to see in just a second that this curve, sadly, is not a boundary. And it's not particularly fixable. Okay. So we're going to use the fundamental theorem of line integrals, and it works out perfectly because this vector field that vector field is a gradient. Now you can check this algebra yourself. I encourage you to do. You really should do this. It'll take you a second. But if you look at this function right here, x squared, y squared, you compute its gradient. Sure enough, you get exactly this vector field. Sweet. So, I mean, it's kind of all over but the shouting. I mean, we know our anti-gradient goes there and there. I just have to plug in the starting point and the ending point. Well, again, my curve is parametrized. I know it's going to start when t is equal to 0, which gives me my a to plug in. And I know it ends when t equals pi. That tells me the b to plug in and plug and chug. Nothing to it. Simple arithmetic. And we're done. Everybody good? Now, let me rephrase that. Aside from the two big details that I totally swept under the rug, aside from that, is everybody cool with what I at least did talk about? And then I'm going to confess my little crime here in just a second. Okay. So, before I get to my confession, look how great this result is. I mean, this theorem's totally awesome, right? I mean, I didn't have to do any real trig. I didn't have to take a nasty antiderivative of a nasty combination of sines and cosines. Just plugging in a couple of points as simple algebra. Amazing theorem, very powerful theorem. Okay, confession time. How did I know from the statement of the question? Keep in mind, this is all that's given in the statement of the question. How did I know that that's a gradient? Right? It doesn't say that f is a gradient. What is it about that vector field that announced itself as being a gradient? How did I know that? Well, there's an answer to that question, and I'm going to show you all in a few minutes here. Second question, assuming that I knew it was a gradient, how did I know that this was the anti-gradient? I just pulled a rabbit out of a hat there, right? So y'all should be wondering, very reasonably, how am I going to know when the vector field is a gradient, and how am I going to know how to find the anti-gradient? And there's an answer to that second question as well. And we probably won't get to that today, but we'll get to it on Wednesday. Okay, before we do that, I need to talk about this idea called path independence. Really cool idea, counterintuitive, I would say. Let me start with an obvious statement right here. If you're going to compute a line integral over a curve, kind of depends on the curve. Well, of course it does. The curve is where you're evaluating stuff. Of course the curve matters. I mean, come on, it's got to matter, right? Now, before we get into that other stuff, let me just to emphasize the silliness. Of course the curve matters. Here's a couple of different curves, C1 and C2. Those curves start and end at the same point even. And yet if you compute these integrals, they are what I'm going to call clearly different. And I'm going to leave it as an exercise. This is very doable. You don't even really have to get your hands dirty. You don't even have to explicitly write out parameterizations and things. Because notice the vector field, for example, let's look along this bottom edge of the square, right? On this bottom edge, the vector field is pointing that way. dr is pointing that way. They're perpendicular. If f is like this and dr is like that, then f dot dr is 0. So on this edge, no line integral. And likewise on this top edge, no line integral. A couple extra little details, good exercise, think it through. But these integrals are different, and again, well, of course they're different. They're integrals on different curves. Why would we even bother to say it? Of course we should expect these to be different. If they were the same, wouldn't that just be a weird coincidence? Okay. All right. So here's the amazing thing. There are some vector fields, what we call path-independent vector fields, shockingly, where only the endpoints matter. The curve in between and how you get from the starting point to the ending point doesn't matter. It's stunning. How could this possibly be true? So anyway, do keep in mind the curves do have to share the same starting point and the same ending point. That is a very important condition, but one curve, compute the line integral over that one curve. Second curve, same starting point, same ending point, compute the line integral over that second curve. And if it is a path-independent vector field, if it's one of these special vector fields, you will always get the same value. Any C1 and C2, as long as they start and end at the same points. Again, kind of counterintuitive. To me, when I first saw this, and I still remember being a college student and somebody, asserting to me that there are vector fields and you pick whatever curve you like, and I remember thinking, well, that's nonsense. Obvious nonsense. Surely I can pick some particularly wacky curve that goes way over here and goes around and does a whole bunch of stuff and creates a bunch of line integral that the other one doesn't do. How could this possibly be true? All right. So to be clear, this is a special property, and only special vector fields have this property. And here is my first example to give you of vector fields that have this property. Regularity issues aside, we do need continuous to make everything work here, but gradients have this property. Gradients are path independent. And in fact, it's pretty straightforward to see why gradients are path independent. So here's how we're going to see it. Now do keep in mind, if you're talking about path independence, you've got to nail down a starting point. You've got to nail down an ending point. And when I say pick any paths you like, it doesn't matter. They do have to start at your agreed upon starting point, and they have to end at your agreed upon ending point. That's very important. So there's one. Here's another curve. Starts at the right starting point, ends at the right ending point. But other than starting and ending, notice the way I've drawn C1 and C2, they're totally different curves. And I claim that the green line integral is equal to the blue line integral. How could this possibly be? Well, key point. Our integrand, for each integral, our integrand is a gradient. This is not just some random integral off the street. This is an integral of a gradient. Flashback to this theorem right here. If you're looking at an integral of a gradient, you can use the fundamental theorem of line integrals, namely the answer, the whole computation for the whole integral, it's just going to be f of b minus f of a. Right? When you're looking at an integral of a gradient. So, well, here we are. Indeed, we are looking at an integral of a gradient. That green line integral is f of b minus f of a. Likewise, the blue line integral. It's a line integral of a gradient. It, too, is f of b minus f of a. And so you can see now, we made a point that these two curves have to have the same a and b, and therefore they will have the same f of b minus f of a. Therefore, they evaluate by the same formula, and therefore they are the same values. Everybody with me? So it's a really clever argument. Very cool fact. Amazing, again, that this is even possible, but cool that it works out this way, that every gradient is path independent. Regularity issues aside. Okay. By the way, it works the other way as well. And again, regularity issues aside, but every path independent vector field is also a gradient. So among appropriately regular vector fields, these two different features, being path independent, being a gradient, two different features of exactly the same vector fields. Every gradient is path independent. Every path independent is a gradient. Okay. Now here's a different way to say it. This is sometimes very useful alternative formulation. Keep in mind, if we're talking about path independence, we got to start at the same point. We got to end at the same point. And again, we have some first curve C1, some other curve C2. Path independence means that these two, these two integrals are equal. Green equals blue for path independence. Now I'm just going to rewrite this statement just to get an alternative phrasing. Instead of saying green equals blue, another way to say that is that green minus blue is equal to 0. Same statement. Okay. Now what I want to do is I want to look at this difference as itself being an integral on a path, a new path. It starts on C1. You can see it says right here, integral on C1. So let's do what it says and go around C1. But then it also says I also need to do an integral on C2, except wait a second, I need a minus sign. How do I account for the minus sign? Well, the minus sign means I'm going to move backwards along C2. And backwards along C2 has me then doing like that. So altogether, saying that the green equals the blue is equivalent to saying that that closed line integral is equal to 0. Closed line integral because, well, it starts and then goes around and then keeps going around and ends back at the same point it started. So this is a closed line integral, and saying green equals blue is the same as saying that that closed line integral is always equal to 0. Another way to say that is that this circulation, right? Remember, a line integral on a closed curve is a circulation. That circulation has to equal to 0. Now, that's just an alternative formulation. There are some situations, or there are many situations, where it's most convenient to think of path independence about two different curves, same start, same end, giving you the same value. Absolutely. There are other circumstances where thinking of path independence as all circulations being 0 is the best way to think about it. Different circumstances. How we doing? Pausing again. Any questions? Okay. Let me give you an example of where we care about the latter. And this is kind of a fun one, I think. Some of y'all may already be familiar with this artist named M.C. Escher. Show of hands, M.C. Escher. Anybody? Handful? Oh, very few people. Okay, a few people, right. But he's a pretty fun artist. He drew things that he created illusions, right? Things that the way he drew it kind of look feasible, kind of look realistic, until you look a little bit more carefully and realize, hey, wait a minute, that doesn't make any sense. That's impossible nonsense, right? And this is a nice example. Looks like some people just kind of walking on some stairs. What's the big deal? What's wrong with this? Well, what's wrong with it is you eventually notice that this person right here And you can see this person is just following that person who's just following that person. And there's this line of people going around, and they're all going uphill and all following each other, all going uphill. And yet they keep coming back to exactly where they had been. And whoa, what's going on there? How could this possibly be? It's not possible. Right? Everybody see how this is nonsense? There's no way that you can keep climbing stairs and keep coming back to where you were in the first place. It's like something out of a horror movie. Right? And then likewise, you have these other people on kind of the inside track, and they keep walking downhill and keep coming back to where they were in the first place. So again, totally impossible. Doesn't make any sense at all. All right, so I claim that there is a point of view on this that we could describe with the math that we just learned. And I think it's kind of a nice take. So let's think about h. What I'm going to call h here is my altitude function. So it tells me how high above the ground. Let's just say how high above ground level we are, wherever we might happen to be. And I'm going to say, let's see here, I will use green for the gradient. I'm going to call that the steepness field, because that's what helps you keep track of how your altitude is changing. Gradient dot, let's see here, I will say dr represents how far I go horizontally. Right? If you know your displacement horizontally and you dot with the gradient, well, that'll tell you how much your altitude has changed. And so this f dot dr is telling you how much your altitude changes with every step dr that you take along the stairs. Is that cool? Everybody happy with that? So let's make a couple of observations here. Well, for one thing, I know that because that's a gradient, we know it's path independent. We know path independent means all closed line integrals are 0. So we know that the grand total, the altitude change has to be 0. Well, of course it is. If you go around a closed loop, of course you come back to exactly where you had been. And if you're exactly where you had been, of course your altitude can't have changed. That's the intuitive part. That's the, well, of course it's got to be that way part. The way Escher has drawn it, though, Escher has drawn it so that each one of these steps that we're taking as we move along here, they all look like they're walking uphill. All of the f dot drs, all of our, you might say all of our dhs, he's drawing all of these f dot drs as being positive. That's the picture that he's drawn. And if these things are all positive, I'm adding up a bunch of positives. I can't get 0. Right? So Escher would have us believe that integral f dot dr is some positive value. We know, of course, that it can't be. So there's kind of the contradiction. Now what's the value of this? Am I claiming to have proved something that you can't just see obviously from the picture? No, not at all. Right? It's perfectly you don't have to know multivariable calculus to be able to look at this picture and say, hey, that's nonsense. Right? You don't need that at all. What I like about this, aside from, well, sometimes it's nice to just explicitly say what the problem is. What I like about it is that this gives you a picture to have in your mind of why this not only is true, but why this should be true. Right? Why should a gradient have the feature that all closed line integrals had better or equal to 0? Answer, if it wasn't, Escher stairs would be possible, and that ain't right. Is that cool? Everybody on board? So this is a counterexample. You might say this is a picture of a counterexample. That's sort of why this really should be true. Okay. Now, let's see here. I think we have time to do this last example, or one last example. Yeah, that'd be a pretty good ending place. Path independence has some nice conceptual uses related to potential energy and conservation of energy and cool stuff like that. And if we had more time, then I'd love to spend a few minutes talking about that. We don't really have that time. But I'm going to say in most cases, computationally, we don't really need it in most cases, because let's face it, if your vector field's path independent, we already know that means it's a gradient. And that means we can use the fundamental theorem of line integrals. And fundamental theorem of line integrals is this awesome sledgehammer. Where was it? Here it is. This awesome sledgehammer that just crushes line integrals. I mean, if I already can do this, who needs a different computational method for these kinds of scenarios? Let's just do this, right? Okay, well, here's the problem with that reasoning. The problem with that reasoning is that in order to be able to use the fundamental theorem of line integrals, I do need to be able to find my anti-gradient, and sometimes finding an anti-gradient can actually be pretty hard. So, in fact, I have several examples on my old exams where I gave students a vector field, asked them to compute a line integral, but I deliberately arranged it to where they couldn't find the anti-gradient. That the anti-gradient is just intractably difficult. It's just too much. Oh my gosh, just too much trouble. Can't do it. So if you can't find the anti-gradient, then of course you can't use the fundamental theorem of line integrals. So what do you do then? And the answer is path independence is in fact sometimes a nice computational tool. And here's an example. Notice we have a vector field that's given here as being path independent. Let's momentarily pretend that we don't notice the anti-gradient. And I'll bet if you looked at it and started thinking cleverly and strategically, I'll bet you could probably dream up the anti-gradient. Let's not. Right? Let's pretend this is one of these examples where we can't find the anti-gradient, but we know it's path independent. And the question is to compute this line integral over the top half of the unit circle, like so. And what are we going to do about this? Well, I guess I could parameterize that curve, but again, lots of trig, and again, it's not that I can't do it, but I'd really all else being equal, rather not. So I'm going to use the path independence. Path independence says, look, as long as you don't change the starting point and the ending point, pick any curve you like. Whatever. Any curve you like. You can use that curve if you really want to. I don't know why we'd want to, but you could. Any curve you like. I like that one. I like nice, straight, simple, straight lines, simplest possible curve I could possibly think of. That looks like the easiest choice to me. Path independence tells me the blue line integral I've been asked is equal to the green line integral that I would much prefer. And therefore, I'm going to say phooey on that blue curve. I'm going to compute on this green curve. On this green curve, notice how easy it is to parameterize. No trig. Furthermore, notice that y is always 0 on this green curve, not on the blue curve. I couldn't do this on the blue curve, but on this green curve, y is always 0. And if y is 0, that's always 0. And furthermore, if y is always 0, it doesn't change. If y doesn't change, that means that dy is 0. And then this integral that I'm trying to compute, f dot dr, is 0, and my answer is 0. And I didn't have to get my hands dirty with any nasty trig or anything like that. Just, clever use of path independence. We changed the question, seemingly cheating by changing the question to something much easier. and then the calculation falls apart into nothing. Okay, good place to draw the line. We'll pick up here next time. Y'all have a good rest of your Monday. See you Wednesday.